In this video, we will see how we can use Mathematica to plot two-dimensional surfaces in a three-dimensional space. So we'll start by seeing how we can plot the torus. And for that, we'll use the embedding equations of the torus, where we'll use the symbols x1, x2, and x3 to actually mean the x, y, and z coordinates embedded points. So the three functions that define the torus, and here they're functions of the independent variables u and v, and r1 and r2 are symbols that will actually later be substituted with the two radii that define the torus. So we press Shift-Enter to evaluate the cell. And we can use these definitions to any expressions that we want. So for example, here, we obtain a list of the functions evaluated for the symbols u and v. But we can substitute anything for u and v. For example, we substitute theta and phi. Then we obtain the same expression, but with theta and phi in place of u and v. And we can see the result in a more familiar looking form by applying the traditional form function here. It gives us output that is more like what we usually find typed in books. But in order to make plots, we need numerical values. So can obtain numerical values by putting approximate real numbers in the arguments of those functions. Then this will be substituted, expression for the functions, and we will obtain here a list of expressions that have approximate real numbers, but they also have the symbols R1 and R2 unevaluated because they have not been defined. So, of course, we can give specific values to R1 and R2, assign them via assignment equations, but we will use another method. We will substitute values for R1 and R2. And you see how substitutions symbols in expressions is done in Mathematica. We use this sequence \dot, and on the left hand side here we have the expression which is evaluated, and then here we have the rules of substitution. So this actually, in plain English, it means take this expression, which is given here, definition of cell input 1, and whenever you find the symbol u, substitute the number 0.3. Wherever you find the symbol v, substitute 0.1. Wherever you find R1, substitute the exact integer 3. And whenever you find the symbol R2, substitute value 1. So after the substitution is done, the expression is re-evaluated, and we obtain a numerical result. So this is a point on the torus when u is 0.3, v is 0.1, and the torus has geometry given by r1 equal to 3 and r2 to 1. We can view the torus by using parametric plot 3D. This function plots a surface if it is defined to be two-parameter plot. we will use these specific values of R1 and R2 just for nice visualization. And we will call parametric plot 3D in the following way. First of all, here we put a list. Let's call it the position vector, the points. So the position vectors depend on two parameters, u and v. And the fact that u and v are the parameters of the parametric plot is defined by those expressions here, which show that u and v are varied between values 0 and 2 pi. It's one of them. Now, in order to make a plot, we have to have numbers we put on the plot. So we cannot have R1 and R2 unevaluated. So we can use this vector obtained after substituting R1, 3, R2 for 1. So this gives us this very nice plot of the torus. And magnify it here. You can use the mouse to do it from different perspectives, different directions. But we can use parametric plot 3D to plot curves expressed in a parametric form. This is a very simple and trivial example. So here, I have to put a list that gives the position vector of every point plotted on the surface, on the curve. And now, this vector depends on one parameter t, whose range is defined here. So, this is the result. It's a helix. You can also view from sections like. So let's now see how we can plot a curve on the torus. So a curve on the torus, it is a one parameter function from the real numbers to points on the torus. So one way to define the curve is to define a function of t that will give us a curve in the coordinate system, u and v. Then we will use the embedding to give us the position vector of the uv point. So if we define a vector as a list here, we can get the first element of the list, that means the function u of t, by asking for element number 1, the v, by asking element number 2. So let's see how to construct the command. First of all, here we define the function that gives us the curve. So u is equal to t, and v is equal to 10 times t, or 10 times v. Then we construct the position vector, the point on the torus. And you see here we use the functions x1, x2, and x3, but now the arguments here are not simply u and v, but they are the coordinates of the curve, the uv coordinate system. So we do that for every function here. Then we look at the curve as t varies from 0 to 2 pi. So we see here a curve that seems to wrap around the torus. Look at it, directions. But now let's see how we can plot this curve on the torus. So Mathematica gives us the ability to take two different graphs, combine them into one. So what we will do now is step by step construct this plot. So first, let's define the curve. So this is the curve gamma. Then I define the plot that will give me the curve as before. So now, you see I use the same parametric plot 3D call that gave us this nice graph here. But now what I do is two things. First, I put a semicolon here so the plot will not be shown. Then I give a name, plot, and this variable here will be a graphics object. So if I press now Shift Enter, the plot is done, but it's not shown to me. If I want to see this plot, I have to use the show function and put here the name of the graphics object. So you see that these two sets of commands have the same effect as the one command had here. But now I can define a different graphics object which is now a surface. The same parametric plot 3D call that we used to construct the torus up here. So again, I put a semicolon here so that the plot will not be shown. In fact, if I press Shift Enter here, it is not shown. If I want to see those two graphics together, I have to ask show to show me both G1 and G2. So look how it is done. We have the curve plotted in the default format on the surface of the torus. Now I can add some style to it, make it look better. For example, change the color and the thickness of the line to make it more visible, but also make torus more transparent so that I can see the wrapping of the curve around the torus. So here is how it's done. So this is the same set of commands I gave in the previous cell, but now I have added plot style directives here. So the plot of the curve will be plotted with this plot style directive, giving us a red curve which is also thick. For the graphics that will give us the torus, I have asked to have the directive here that the opacity of the surface is at the 0.3 level. Then, when I show the graphs, I add some options here, make the graph look nicer to me. First of all, I ask for the whole plot range to be shown of the plots. Then I want the axis and this nice box, puts the surface inside, to be removed. So this is the result. And now you can see the curve as it wraps around the torus, and you can, for example, also change the level of the opacity. Let's say, put 0.6. 0.8. Make more clear what part of the curve is front, part of the behind. So let's play this game and look at specific curves, the torus. So let's follow coordinate curves, and let's look at the u equal pi over 3 line. So all I have to do is repeat the same commands, but now I define the curve to be this one. So you see this curve keeps the u value equal to pi over 3, and the t value will be taken along the full range in 0 and 2 pi. So press Shift Enter here. See that this will give me one coordinate line here. And I can move it around by changing this number here. Make it pi over 4. We'll get a different one. Pi over 2. Get a different one. So if I want to see how these coordinate curves move around as I change the constant value curve, and use the function manipulate. So what I will do is I will take these commands and insert them into the manipulate function and making this constant value a parameter. So here it is. See, this is the manipulate function, and it ends here. So the manipulate function, you see from this list, that has a parameter called const, the constant value that I will put for you. And then the plot will be made each time for a given value of const in this interval, 0 and 2 pi. So when I will start showing this plot, we'll get this result here that shows me this coordinate line for const equal to 0. That means for u equal to 0. Now I can move to different values of u by either sliding this here. See that this curve is moved around. Or I can ask for a specific number for it, 5.4. Press enter. Or 6.1, press enter. Or I can make it play like a movie, but it's not so nice because it doesn't have enough time to draw the curve with its isoline. But generally for manipulate, you can play or move forward to different values. Now, let's do the same for the v equal constant values. So now I will define v of constant values. So I do the same command, but now the curve has the parameter t, and the const refers to the v value. Const changes from 0 to 2 pi. So for a given value of const, I will get a v equal constant curve, torus. So get larger if you want. move it around, angles, and you can change the value of V by sliding. See how it is moved. Yes, you get the point. Okay. Let's move to a different example. Cylinder. The parametric equations here. Evaluate them. Enter. Not same as the torus. And we can also draw the cylinder together with a curve using similar commands. So this is curve in the UV coordinates, and the parametric plot equations are exactly the same as before. What we get see the cylinder from the angles. And we can see the U and V lines by doing a two-parameter plot. Sorry, two-parameter manipulate plot. So you see now we define the two curves, the U curve and the V curve. One is defined by having U fixed to U0. The other one is defined by having the value of V fixed to V0. And those values change from 0 to 2 pi. Then we have 3 graphics objects to show, one for each curve. So GU, the graphics as you see for the gamma U curve, GV for the gamma V curve. You see here, cylinder, it's 2 coordinate lines, and you can change the numbers here. Step forward. The red line is moving around. And then by stepping forward the V0, the blue line is. Okay, let's look at another surface, Klein bottle. Now we have an immersion of the Klein bottle, not an embedding. We use the formulas that you can find in the Wikipedia lemma for bottle. These are the equations. Slightly more complicated than previous examples, but straightforward to implement. So, as we have said, the class, it's not possible to embed this in R3. and immerse it in a tree. If you do a parametric plot, that will be this. Evaluated this plot, this cell, this one, and I obtained this familiar looking shape of the Klein bottle. As you can see, it starts from here, then it goes into itself. The gluing here. Now, let's see how this surface is constructed as we increase U. So we will use manipulate again. So now we make a parametric plot of the above surface. But now we don't use the full range of U. We go up to a value U max, where U max is the range of 0.4 and pi is the maximum. So this is the result. We make the plot for U from 0 to 0.4. You can see how the Klein bottle is formed by increasing U max. So you see the bottle becomes longer and longer. You have to do twisting around, turn. Again. You have to enter inside the bottle. Now you see how these two circles now met can be glued in the same direction. Form the Klein. Let's see how the surface is formed as we increased V instead of U. So now we make a parametric plot for U taking values over the full range, 0 to pi, but V taking values from 0 to V max. And V max ranges from pi over 3 to pi. So this happens when we stop pi over 3. And as we increase, start seeing circles to be formed. Looks here. Starts closing. So this is half the way. That is V max equal to pi. You do it yourselves up to 2 pi, you'll see how the Klein bottle will be formed. Now, let's draw U and V isolines. So, as we saw in the lecture, the U equal U0 curve is a circle. And let's plot the curve when U takes the constant value pi over 4. So this is the curve to be plotted as constant U, and T varies over the range of T, of U, sorry, over the range of V. So now you see the Klein bottle, and this is the closed loop we obtain when U takes the value pi over 4. So change this to pi over 3, different one. Again, you may use manipulate to see how this curve is around the full Klein bottle. See, we arrive at the value U0 close to 2 pi, get close to the point we started from. Now, let's look at the V equal constant curve. This is trickier because you remember that when we made when we showed when we moved along the V equal constant line on the square representation of the Klein bottle, then we ended up at a different point. You can see that the immersion. So here, give the constant value V equal pi over 3 curve, and we plot the line 0 to pi, which is the full range of V. So look, this curve starts from here, goes around, ends up at a different point. So look carefully. See here, obtain 2 different points here. But you also remember that if we repeat this procedure, then we end up at the same point. So the curve will close if we go twice range of parameter V. So is put here T max now to be equal to pi. See that indeed now the curve closes. So again, it moves around once, ends up at this different point, but sorry, at this different point here. Sorry, at this different point here, and then it goes on like this around. It meets the original point here. So you see, for that, it has to go around twice. So now let's do a different type of graphic, much simpler, but as you will see, it requires some work. So let's look at the sphere and the map that we use to project it to the coordinates UV and ST. So remember those coordinate systems used. Have the theta and phi coordinates. Now rename them as U and V, although they're not objective. So the x coordinate is sine U cosine V, y coordinate is sine U sine V, the z coordinate is cosine U. So that defines us the embedding here. Make a similar plot. Some isolines. So see here, theta equals constant, isoline. Here a phi equal constant, isoline. We can move them around. Changing the values of U0 and V0. Okay. That was easy. Following. Now, you remember this figure from the class? We use the north pole to project P on the xy plane and obtain coordinate P. So let's try to make this plot using Mathematica. Such plots are not made from the beginning, just we will make them plot step by step. So let's use theta and phi to define the point here. And let's choose values pi over 4 and pi over 4. So the x, y, and z coordinates, point P, are given by the symbols xp, yp, zp. Then use this projective map to obtain coordinates u and v for the point P, which are equal to x by 1 over z and y 1 minus z. Okay. So plot the sphere. That's given by this parametric plot. See this plot by using the show function. And that simply gives us a sphere. So let's add the elements of this figure here one by one. So let's first put the point P. How will we draw the point P? We will put a small sphere at this position and give it some style so that we are able to recognize. So let's add this point. Here is a graphics object. All. So we use the graphics 3D directive. Put the point there. So what the graphics object is a sphere. The sphere here trying to have a center at xp, yp, and zp, and a very small radius 0.025 to have something that looks like a point. Then we ask this sphere to have red color here, and then top of it to be marked by text, which will give it a name, point P. This text will have style, be given by a bold letter. It will be black in color, and it will be positioned this point, which is the position, the point P, but moved a little bit far away by this arbitrary 0.05, so that it is visible the figure. So now, if I want to see this point, I have to add here the name of the graphics object. Press Shift Enter. So look here. I have the sphere and the point located at theta equal pi over 4 and phi pi over 4. Now, since I want to project this point on the xy plane, better show that plane as well. So I defined a new graphics object. I call it GP, which will show me part of the xy plane. I have to put it here as well. Okay. Now, see the sphere cut by the plane. So here I made this plane less transparent, but distinguish it from the sphere. Now we need the line. Sorry, first, then we need the north pole. Pole also be a point similar to P. So here Shift Enter. Also show it. You see the 2 points, the North Pole and the South Pole. Then I want to draw, I want to put the point where point P is projected when I consider the line connecting N and P at the point where it crosses the plane. So here, so drawn like a small sphere, call it GUV. And you see now those 3 points that are supposed to be on the same line. Okay. This point here has been defined to have coordinates UP and VP. pole has coordinates 0, 0. Okay, so now let's draw the line that connects those 3 points. How to draw this line? The parametric plot. So the points of the line segment between n and u given by the vector, the sum, position vector pole, plus the vector n starts at n and ends at uv, multiplied by a parameter t that goes from 1. So if you add those 2 vectors, they parametric representation. Let's see this line as well. Okay. And indeed, this line starting at n, going through p, ending so without going through all the details, you can enrich this graph by putting more points so that you can compute things. Show you the final results here. I add all those points, M, R, K, V, and all those lines connecting them. What is this? So here is the point P, projected onto UV. Then if you want to calculate the coordinates U and V, you simply project this triangle, z-plane, compute U from the coordinates V, which are now here, Z, X. We're working on this triangle here with the relation that we showed. Show you the set of commands once more. But it is indeed a nice exercise that you can do patiently, adding the graphics one by one. First the points, then the lines. Then you will be able to become experts drawing such plots. Okay, one more example. Möbius strip. Here is parametric representation strip. Find this in Wikipedia. So here you see that I do not define separate functions x1, x2, and x3, but I define a vector, position vector, directly. So you see those 3 components. The first component is here, the x coordinate component of the position vector, y component, and the z component. Now, I will also do some differential geometry on this surface and compute the tangent vectors, the u and v directions. So all I have to do is to differentiate this expression with respect to u and v respectively. Then I will obtain new functions of u and v that will give me the tangent vectors. You can also compute the normal vector to the surface as the cross product of those two tangents. So let's see the results. So you see here the components of the tangent vector in the direction of u, direction of v, and the components of the normal vector. So first, let's work we did before. See some isolines. Equations here. Have the two curves B exactly as we did before. All we have to do is to be careful and put the range of each parameter to be correctly. Otherwise, the commands are exactly the same before. So here you see the result. See the two lines. If you move this red line around, the other line move. Now notice that I have drawn the v equal constant curve in two different segments. One is magenta, the other is blue. The reason is that, as in the case of the Klein bottle, here we make an identification in the opposite way. So when we move around once over one isoline, we end up at a different point. And we have to go around once more to meet the original point. So actually, these are two isolines, not one coordinate. So let's now try draw the vectors that we defined before. So let's start drawing the same graph before, and we choose particular values for the u and v coordinates, the fixed isoline. So I will see a plot that is similar to the one I created before. But now I want to add those vectors that I defined here, the tangent vectors and the normal vector. So I will define them as graphics objects, which are arrows. So tangent vector u direction is defined as a graphics 3D object that is an arrow here, where the arrow is located at this point. The arrow extends from this point, which is the position vector at u0 plus 0.1, just to move the vector a little bit forward. And the end point is the position vector plus 1/2 the tangent vector. So I put here arbitrary scale just to make the plot look nicer. So add this here. See that an arrow representing arbitrary scale, of course, tangent vector has been drawn at this point. Okay, this point is at the value 0 plus 0.1. That is why it does not coincide the red line here. So you see this is in the tangent direction. And similar way, draw an arrow in the v direction. So now I draw an arrow that is starting from the same point, x, to a point that is defined by x plus now 0.8 times the other tangent vector. Okay, this is an arbitrary scale, as I said. Make the plot look nice. So I add this graphics object to the show function. Now you see I have the vector that is tangent in the other direction. The vectors are on the surface, tangent. Now let me draw the normal. Similar fashion. Draw another vector here, perpendicular to the other. Here. And now you see here three vectors mutually orthogonal to each other. Normal vector pointing downwards. So let's now try to make a plot and see how this set of three orthogonal vectors changes as we move around this direction. That use manipulate call. So I will wrap this command around the manipulate function. So this is the one. It's exactly the same plot that we created here, except now that u0, the position of the origin of this the origin of the three vectors is a parameter that varies by the manipulate function from 0 to 4 pi. I will also use the same graphics directives to draw a fixed basis at u equals 0. Okay, so let me do that. So you see now what happens when U0 is 0, the two sets of triplets, two triplets of vectors are on top of each other. But we can move the other one around by moving this point U equals 0.26. So now look, the normal vector has been drawn a different color, it's blue. And compare it with the normal vector at the original position. Also see that this vector here moves around this curve here. And this one is also so that it's always along the other coordinate direction. So let's move it further. You see that the two normals are quote below. Then moving forward. Now look what happens as this goes around. Magenta vector downwards, whereas the blue one starts being quote upwards. So you see, they come around, two things happen. Here's the two linearly independent vectors start getting close to each other. Now this vector here will continue this direction, but this vector here now shows in the opposite direction. As a result, the cross product also points in the opposite direction. So when I move it once more, when they meet at the same point after the strip, this vector coincides with this one, but the green vector is opposite to this red vector, and the magenta vector is opposite to that vector. This is why Möbius strip is an example of a non-orientable surface. Because if you move around the basis, when it meets around the closed circles, closed loop, such as the one that we just followed, then comes back instead of being right-handed, left hand. Normal vectors point in the other direction, so we cannot use normal vector here to tell us one side of the Möbius strip is same or different. Start painting surface green, go around, start painting green the other side. Because of the opposite identification. So let's move further. Here. You see, as we go around for a second time, two bases meet, their orientation agrees. So is normal vector.